All right, this is the HVR110 evening class, week 4, lesson 2. This is going to be our second of 3 lectures. We're going to be going over chapter 12. Right. Go ahead and get started. Finish up chapter 12, and then we're going to get into chapter 13. So right here at the end of chapter 12, it talks a little bit about heating controls and stuff like that, which is what 13 is all about. So we'll probably go through that pretty quickly because we're going to go more in depth when we get to the other slides that have more information for you. So last thing at the end of the last session we talked about was delay on make and delay on break timers, on how those operate and work and everything like that. Now the other thing we've got is specifically an anti-short cycling device. So I said that electronic timers can be used to prevent short cycling, which is basically the system coming on and off really, really quickly in succession. It makes the contactor sound like, it sounds like a machine gun. It goes clack, 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 clack. It just constantly in and out really, really quickly. And that's extremely bad for the system to do. Even if it's not doing that level of short cycling, if it's just constantly having to come on, shut off, come on, shut off, come on, shut off. Like older systems, they would have it where there were only a couple of controls to stop a compressor from coming on. Typically, it was one control was to make sure that the compressor didn't overdraw amperage, and the other control was to make sure that the compressor didn't over-pressurize the refrigerant system. So if it overdraws on amperage, it just waits for the system, for the wiring to cool down, and then it fires on again. And that could take a matter of minutes, could take a second, could take just a couple of seconds. But once it cools off, it'll fire right up again. So it'll shut off and then fire again. It just keeps starting up every 6 to 10 seconds. And that causes a lot of issues, as you guys can imagine. Imagine if you had it where someone, instead of the bus driver, instead of keeping the bus just running, decides, well, you know what I'm going to do? Every time I try to move this bus, I'm just going to turn it off, turn it on, move it 3 feet, turn it off, turn it back on again. It would take forever. It would cost a ton of fuel. And it would wear down all the components, all the parts, all that starting, stuff that you got, all that battery power and everything like that would just be sucked up. For us, what happens to us when we're short cycling is we have it where the motor is taking on more and more electricity, and it's not being given time to actually dissipate all of the electricity out of it. And so with that electricity comes heat. So it builds up electricity, builds up excess heat, and the system just burns itself out. Is a very common thing when it short cycles. You'll have it. One of those common problems that comes out of short cycling is a grounded out compressor, which means you have to get a new compressor, which means the heart of your system's getting replaced. It's like if you tell someone with a car, hey, got to get a new transmission or a new engine, we got to do what? Yeah, got to get a new engine, got to get a new transmission. Sorry. It's some people will say yes. Most people will say, I'm just going to get a new car. I'm going to get a new air conditioner. But to prevent that from happening just because a system has an issue with airflow or has an issue because of a fan motor not working or something like that, the short cycling device is really just there to prevent and make sure, okay, let's have a set amount of time that this compressor and this system have to wait prior to a system, trying to fire up again. So it's very much just like the other electronic timers we've seen before. It's just that it's specifically purposed for short cycling. So it's not so much a time delay sometimes, as some of it will be sensitive to current, but typically it's going to be time, as most of them. They'll still be able to be set anywhere from, like saying, 30 seconds to 5 minutes. 5 minutes is going to be your standard. So if you set your timers to 5 minutes and you start watching it, it kicks on at 4 minutes, might have been only set to 4 minutes. But if you set it to 5 minutes and you wait for 5 minutes to go by, and nothing comes on, you know something else in the system is not working still. So it's not, you know, at that point, you're not saying, oh, it's the short cycling device or the time delay that's causing it not to turn on. It's been 5 minutes. Something else is making it not turn on. And that's just an easy way to eliminate that from being an issue. So again, third time tonight, solid state devices. We're talking about control boards. We've got a lot of different ones we're going to see used. They are used in a lot of different ways for single phase and for 3-phase motors. So remember, with a single phase motor, you've got power coming in. It goes to your run and your start windings. And then ties back to common. All right, versus a 3-phase motor, which we'll get more into, has got it where, oh Lord, please don't judge my artwork. It's very, very bad. These are supposed to be motor coils. I don't know if anyone's getting that. I'll call Picasso up. He'll think my stuff's great. So 3-phase motors have got it where it's going to have 3 legs of electricity, leg 1, leg 2, leg 3, or ABC. And then your single-phase motor has basically got it where it's, ooh, I should erase some of that. Has got it where it's going to be a leg of power coming into into your run and your start windings, and then they're going to connect back to neutral on the other side, basically. These kinds of controls are what we're going to use to control both of these types of motors. You can use solid state devices. They're used for both. It's just going to be different things that they're used for and to control and watch out for. So we talked about overload protection the other day on Monday. Overloads, most common thing we can have go wrong with the system is you know, that system overloading or overdrawing on amperage. It's going to have it where it's got a lot of energy going through it at one time. So to prevent that from, like we were talking about before, heating up, overheating, damaging our wiring and components and everything, the overload is really there to make sure that when that level of electricity is present and comes through the system, we shut the system down before it gets to the components. There's a couple of different ones we can see used. There's the ones that are going to be for, you know, typical things like we talked about last time, a fuse being the most common overload. But they've got electronic control overloads that will, the board basically is going to react to and stop power from flowing through. And this will be resettable. It'll be able to happen multiple times. And usually it'll also give, and it'll log that information of it shutting down into its data bank or into its error code. It'll say, you know, the error code, that LED flashing would say something about, hey, overload at compressor, overload, you know, detected coming into condenser fan motor or whatever device that it's trying to protect. These are really, really efficient ways to protect a system from an overload, which again can be a major detriment to its operation and can literally destroy a system. As if you throw way too much electricity into it, it's just gone. So single phase protection, what it's talking about here is in a 3-phase motor, you have it where you've got 3 sine waves of electricity that are flowing back and forth that are out of sync with each other. They're just a little bit out of sync. The problem can occur where they get in sync with each other and they become a single phase of electricity. When that occurs, the motor will not turn, the motor will not work. Nothing will work on that 3-phase electricity. it has to have those three legs being out of sync with each other in that perfect method and everything like that, in that perfect rhythm. So if electricity gets a little out of whack, if that rhythm gets messed up, then the system will shut itself down and will wait until it can, fix the problem or have it where the three phases are returned back to the system so that it doesn't keep firing up and sends the same voltage into a motor all at once, all on the same sides, or on all sides of it, and then just basically it'll make this kind of sound that just goes, and that's it. Single phasing, not a super common thing unless you're working with commercial systems, because again, this has to do with a three-phase system, which you're only going to see commercial or industrial application. You will not see three-phase electricity or three-phase motors in any residence that I've been in, or in any residence in general, unless they've got a house that, I'm talking off the charts money, where they've got three-phase electricity being run to their house. That means they probably got like an elevator installed or something like that as well, because usually that's about the only other thing that most people would have in a home that would require three-phase electricity. So just depends, but most of the time, pretty much everyone residentially, it's just going to be a single phase. It's just easier and it's less dangerous, so that's one of the big advantages of it. So phase reversal, this is the other option, or the other problem that can occur with three-phase electricity. When you all learn about three-phase motors a little bit more, you'll learn that depending on how you wire up a three-phase motor and which phase is wired to which leg of the motor can actually affect the rotation of it. So if I've got it where I have a phase reversal situation going on, basically what would happen is I have, let's say, my motor, I've got, leg 1, leg 2, leg 3, and they're hooked up to terminals 1, terminal 2, and terminal 3. Now, I got the same motor sitting over here. All right. Now, what's going to happen is if I have it going with the electricity how it is, this motor will rotate clockwise. But if I switch, keep my terminals the same, but my phases switch, all right, so a phase reversal, that's what this is talking about, then all of a sudden now my motor instead goes the other direction. Now it says does not cause a problem. It's true. Doesn't cause a problem. The motor will keep running and the motor will be fine. The problem will be is you won't get any heating or cooling. Your fan motors are all going to run backwards. So your fan that would normally move air through a building is going to throw air back into a building, basically. That blower motor is going to go opposite direction. For a compressor, it's going to throw refrigerant in the wrong direction. For an inducer draft motor, it's going to pull the flue gases out in the wrong direction. So that's what will happen. Now, will the motors be damaged? No. The motors will generally be in pretty good condition, but what will happen is the system will shut off because it's going to try to start up and realize, well, hold on a second, I can't actually move the air in the right direction. I can't move the refrigerant in the right direction, and my thermostat's not being satisfied, so I just need to shut the system down for the time being. But the phase reversal system makes it so that instead of that occurring, this actually stops that from happening, and you don't have to worry about the motors running backwards, basically. So phase reversal protection, again, very important for a three-phase motor. It's going to be a very common protection device you're going to see if you end up working on commercial and everything like that. I'm going to send out a link probably tonight to show you guys what a phase reversal protection component looks like on a system, just so you can at least get the visuals for it, because we don't have any at the school or anything like that, because even at the school we don't deal with three-phase electricity. We all have single-phase electricity and single-phase motors as far as operating. We have some three-phase ones, but we don't have the power for them. So So multifunction electronic motor protectors, we've got a lot of different things you can see right here. Looking at basic stuff we'd see for just about any other motor or component. We're going to see current unbalanced. So if we have it where one side of our motor, the windings, if the resistance changes or something like that, if it increases or decreases, that'll change the amperage on one side of our motor versus the other. And that will make it so that the motor actually rocks a little bit, because now the magnetism created by that amperage is uneven. And so the rotor inside is going to get pulled unevenly. And this is a very common thing you'll see. You take apart one of these motors that's had this happen to it, you'll actually feel on the rotor, you can feel grooves on the side that I got pulled into and was grinding against when you take those rotors out. If you get to that point where you're really bored on a summer day and you decide, I'm just going to take a condenser fan motor or a blower motor apart. Because there'll be those days. Usually not in the summertime. Usually it's in the fall and the spring. Especially time like right now, pretty much everybody's either got their heat running that's been running all winter, or they're cracking a window, or they're just putting on extra blankets at this point because we're at that ebb and flow back and forth between hot and cold. All right. So like I said, basic number of things that it's going to control and look over and protect. Only other control that's going to be that we're going to see a lot of, and y'all will get a lot of time with this, is going to be when you take your heat pump class. You'll learn more about it. Is your heat pump control module, or your defrost control board is what it's typically going to be referred to for the one specifically at the outdoor unit. These control boards are going to be looking at a number of different things. So for our basic, okay, so we got a compressor, condenser, evaporator, expansion device, and evaporator. All right. So these four components right here in this order, that's our typical refrigeration cycle. It goes from the compressor to the condenser to the expansion or metering device, and then into the evaporator. The difference, there we go. The difference with the heat pump is what it does is it takes that refrigeration cycle and it runs it in reverse and makes an air conditioner into a heater. This is the most common way to heat in the state of Virginia. And the reason is we are in heat pump territory. We're pretty much in the prime location where they work really, really well. Heat pumps typically stop working very efficiently once your winter temperatures get to an average of about 40 degrees or below. Virginia, we have most areas are above 40 for the average winter temperature. So we're not dealing with super, super cold all the time. And it makes these systems run really efficiently. So one of the things that happens is with this heat pump operating, and you may have seen this actually at your home or where you live, it's got it where if you've been outside in the wintertime and you look outside, your heat's running, and if that outdoor unit is running, you might have seen ice build up on it. It might look like big white ice all on the outside of that outdoor air conditioning unit, that condenser coil. And this is what causes a heat pump to lose efficiency and not be good once it gets to below freezing temperatures, typically, or below 40. And this is what a electronic control module is going to watch out for. So it's going to watch out for that ice buildup. And it's going to be looking out for that and making sure that when it builds up ice on it, it'll go into a defrost cycle and it'll melt that ice off of it. It'll also be able to anticipate that temperature that it's got going on outside. If it's got an outdoor temperature sensor with these controls, this will actually let it know, yes, you can turn it on to the heat pump mode, or no, the heat pump's not going to work. We need to turn on either the gas furnace, or more typically, we're going to turn on that electric heat. You probably had it before where the heat's kicked on, maybe it's the first time of the season, or it's a really, really cold night, like the temperature drops down to the 20s, and you wake up and you smell that kind of burning smell, and you're like, what is that? And that's the electric heat kicking because it's gotten too cold outside. The heat pump can't operate, and the system's told it, hey, don't even try. Just turn on the electric heat and keep that going for now. So that's how these things are going to be operating and everything like that. But again, heat pump control modules, y'all will get more information about them and how heat pumps operate when you have the whole class on heat pumps. So I don't want to go too far ahead, but the main thing to understand is we're still trying to make sure that our system operates efficiently and that it actually gets all of our heat. Oh, good Lord. It gets all of our, can I get rid of this thing? No? Okay. I just put text up that I can never get rid of. Okay, there we go. Haha, figured it out. Sorry. But yeah, the heat pump is really going to be there basically to provide heat for a home without having to burn fuel or anything like that. It's just going to be electricity. So gas furnaces, we'll talk about in a little bit. They've got a lot of different safeties for them. There's a lot of controls and modules. Typically, it's called an IFC, an integrated furnace control, or an IFC board, integrated furnace control board. And that's what you're going to see a lot of times for a gas furnace as far as what kind of control board is it going to have inside of it. And it's going to be operating and controlling a lot of different factors. One of the big things is the order of operations to make sure that the furnace comes on in the correct steps. So that way you don't have, let's say, your igniter coming on after you've turned gas on. Instead, you want your igniter on before the gas starts going. Sort of like, imagine if you had it where you wouldn't, you had a gas stovetop and you turn the dial, and then as you turn the dial, it doesn't start clicking until, a lot of gas has already been released out into the room. We don't want that happening. Same kind of thing with our furnace. It's going to make sure that it's doing everything in the right order. It's going to make sure to, ignite pilots correctly. If it's got an automatic pilot, an intermittent pilot, or a standing pilot. Again, things you're going to learn more about. And so all these different things is what it's going to look at to make sure that that gas furnace is burning, operating, and heating properly. That's the big thing. And then with the modern ones, again, it's going to modulate and control. The modern gas furnaces go beyond just controlling the speed of your fan motors and your, just your fan motors, because that's all that's running on those. But it's also going to control the speed of a gas valve and how much gas is coming through to be burned and everything like that. So these are getting really, really cool. Oil furnace. The big thing with an oil furnace is, first of all, this is the dinosaur. All right, this is how Grandma and Grandpa had been heating their house for a long time. If not this, they probably used coal. They might have had natural gas or propane, but oil, man, been around for a minute. You got a whole class where we just cover oil furnaces, but the big thing to get with it is it's got a weird, unique safety called a CAD cell. So a CAD cell, CAD stands for cadmium sulfate. You don't need to know that, but the CAD cell, what it's going to do is, as opposed to any of other switches that we've looked at so far, any other switches you've seen in the class have reacted to either a manual switch, they've been temperature controlled, pressure controlled, they're looking for a float switch for a water level, or something like that. A CAD cell, however, looks for light. Literal light is what it's going to look at. And you can actually test it and test resistance on a CAD cell and see if it's working by introducing and denying light to it. So you take a CAD cell out, it's going to have two wires sticking out of it. You put your meter, you put your two leads on either side of that, you set it to resistance, and if you cover it with your thumb, you cover the end of that CAD cell up and you make sure that it doesn't get any light, because it's a very, very small part and everything. You can cover it up with your thumb. It's about the size of a, really small. Trying to think. It's an easy thing to put in. Honestly, it's probably the size of like really, really tiny USB drive kind of thing. It's got it where you cover that up, you're going to see that resistance go way up. But as soon as you take your thumb off and you shine a light directly into that CAD cell, you'll see the resistance drop way down. And that's how it works. It literally just watches to make sure that there's light. For an oil furnace, this is how it says, yeah, I know we've got a flame in the system because there's light, you know, unless someone's down in the oil furnace heat exchanger with a flashlight trying to trick it or something like that. So that light is proof of a flame, and then that's a safety. It's trying to make sure, because if it doesn't see the light and it doesn't see that, then it knows, okay, stop pumping oil into the system, stop trying to spark and ignite, because we're just wasting fuel and we're causing the dangerous, you know, safety situation. So CAD cells, again, very unique to the oil furnace, but they're very, very useful for how much heat they produce, as far as compared to gas furnaces or other combustion sources we've got. So I talked about it early at the beginning as far as a way to troubleshoot these electronic controls. The main one, black box approach. Check and make sure you've got high voltage coming in, make sure you've got low voltage coming in, and look at your wiring, look at your board, figure out where that voltage is supposed to be going, and see if it does. Because the voltage comes into the board and it's not leaving the board and the board's not sending it anywhere, the board is probably your issue. Other things you're going to look for is easy stuff, like any burnt or charred thermoplastic or section of the control board. If there's any, you know, resistors that are burned up or anything like that, that's going to be a big issue, and you're going to want to, you know, that's get a new board. Other things like saying here, don't forget, always look at those fault messages. If it's got an LED code, some of them will have an LCD code where it looks more like old school digital alarm clock, and it'll just send a number like 34 or 7B or 8C or something like that. And again, you just go to the diagnostic sheet, and it'll tell you what that code means, whether it's, you know, a motor not working or a switch not operating or something going into a fault, or it could just say system not operating, and it's not going to give you any help because some of them do that. So that's pretty much everything to do with electronic control devices. Again, remember, they're going to be used in pretty much everything for heating and refrigeration. We're seeing them used in a lot of different applications, but when it comes down to it at the end of the day, it's really just understanding that that control board is your main thought process, your main thinking power, the main control for everything going on with a modern system. So go ahead, get right into 13. So again, getting right into unit 13 or chapter 13, sorry. So heating control devices. So we just ended chapter 12 talking about pretty much heat controls, heat pumps, gas furnaces, oil heat. Didn't talk anything about boilers, weirdly enough. But heating controls, we've got it where there's going to be a number of different things we can use that are specific to the heating control side of HVAC compared to air conditioning controls. The biggest thing is just understanding that we've got it where the heating controls have a unique thing as far as a safety they have to look out for that air conditioners don't. Air conditioners typically don't have to worry about overheating except for at the outdoor unit. Heating systems typically have to worry about overheating at the indoor unit greatly, because if anything is to go wrong at that indoor unit inside the house, in the ductwork, in the walls, and it has to do with overheating, it's not like it is at an outdoor unit. Outdoor units are typically a little bit away from the building, a little bit away from the walls, all that kind of stuff. They're not going to be super close to a lot of stuff. But the indoor unit is going to be directly connected to ductwork. It's going to be surrounded by lumber typically, either beams up in an attic, or and rafters, or it will be you know, in a crawl space down there with all the wood slats and everything like that. So that wood, that heat can very much lead to combustion taking place when we don't want it to. By having heating controls, we can basically provide a safe way for combustion to take place without having to um, uh, without having to worry about overheating taking place throughout a system, whether it's electric heat or gas heat. They're all going to be requiring some level of safety control. And then, of course, efficiency is the big thing on the new ones. So um, right here, energy sources used to supply heat. You've got it where your only way that you're going to supply heat to a system is either through gas, electricity, or oil. And by oil burner, it's not talking about like motor oil. It's not burning 5W20 or anything like that. Fuel oil is what it's talking about. Fuel oil is literally just diesel. It's a diesel with red dye in it. The reason why they have to have the red dye is for tax purposes. And if you ever drive a diesel truck, they will not let you burn fuel oil in it for your fuel, even though it's the exact same chemical makeup. If you do that, you will get in big old trouble. Same with burning diesel in an oil furnace. You don't want to be doing that either. So those are your four sources of heat. Well, three really. Atomizing and vaporizing burners. You're really not seeing vaporizing used anymore anywhere. It's pretty much all atomizing burners. Vaporizing is older of the old. It's not, I mean, oil furnaces themselves are an old school technology. They're a much older form of heating, but the vaporizing versus the atomizing is even older than that. So that's some ancient technology. All right, so heating fundamentals. You've got where there's going to be three things you're either heating in a house. All right, heat's going to travel through air, through the ductwork. That's the one most of us are most commonly aware of as far as in the state of Virginia. Most of the time, heating is done through air-to-air means, which means it's going to take air in, it's going to heat that air up, and it's going to move that heated air out into our structure to heat up the air in the structure. So air to air, that's all that's going to be the interaction between the two things. What's the thing that's hot? What's the thing that's cold? Air to air. Another common method you're going to see in a lot of places in Virginia will be, now not as commonly in Virginia as some other places, but you'll see water methods, boilers, hydronics, where it's going to be hot water is moving through, and that hot water radiates out into the air. So it's a water to air, heat exchange. It's very, very popular because you can carry the same amount of BTUs through a 3/4 inch copper pipe as you can through a piece of ductwork. I think it's 6x18. Can carry the same amount of heat as a 3/4 inch copper pipe as far as the hot water in it, everything like that. So heating by water is extremely energy efficient and can be, but it requires a lot of piping. It requires different skill set kind of things sometimes. Lastly is steam. Now, steam is not seen in Virginia. You're going to see it if you go out to the mountains, if you go over to like, out in Farmville, over in Lynchburg, places like that, you're going to see steam boilers used pretty regularly. Steam boilers, if you've ever lived upstate in New York, Maine, Pennsylvania even, where it gets really cold, heavy winters, if you lived out in the Midwest area, you've probably dealt with a steam boiler in a house before. They've got massive cast iron radiators usually that take up a lot of space. They make a loud hammering pinging sound when they start up. It's a ping, bing, 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 bing. It's really, really annoying. And that's typical for the steam systems. Now, they're not super popular because steam requires a lot of heat to be generated in order to produce steam. If you've ever boiled a pot of water, you know how long it takes. If you leave the lid off and everything like that, it just takes a long time. Even with the lid on, it takes some time to get that water to turn into steam. But these different methods that we have for heating, it's going to be based on the application. What have you got? You know, for residences, air to air makes the easiest sense, whether it's residential here in Virginia or residential up in you know, New York or a bunch of other places. Air heating just makes sense. But for commercial applications and industrial, you pretty much always see it's going to be water and steam. Those are the two things. You go to basically any high-rise building in any city, and it's going to be using its heating system. It's not by air. It's going to be by water or steam. I know I was in a building the other week that has like 16 stories, and they had 16 boilers, one for each floor. And these were not small boilers; these were massive. So it was pretty intense, but it was awesome. It's really cool because it was all these controls. But that's what you're going to see a lot of times. Now, the water heating as well, you can do it where you can you can have an air to water heating system where inside of your ductwork you can actually put you can put a coil with hot water running through it and a fan behind it, and as that fan pulls air from inside the house across that coil of hot water, it'll heat up and then it'll move that heat out through the house. So there's a lot of different methods we have for it. Basic controls, again, you're going to see a lot of them used for various things, but the big one really for all of them, they're going to have some sort of fan control to tell it when it needs to turn the fan on and off, and then a safety control for overheating or temperature rising too highly. So for the fan kicking on and off for that blower motor, that's going to be a very, very common one. We'll talk about in the next session probably is the fan switch. It was an old school method that we had, but we have the modern thing nowadays that works basically the same idea. It's just, as opposed to waiting on a temperature sense from a bimetal helix coil, it's, you know, an electronic signal digitally sent to a control or something like that. Again, those kinds of controls, the blower motors, they'll have it where this allows for the fan to be in multiple speeds based on what kind of heating or cooling system it's doing. You know, is it in heat mode? Is it in cooling mode? And then also it will allow for your heating medium to actually heat up before the blower fan comes on. You know, because if a heat exchanger starts heating up and starts burning fuel, and that blower fan comes on right away, it'll actually cool it off, and you won't get any heat moving out through the building or through the structure. So having that level of control makes things a lot easier for us as far as trying to make sure that the heat is actually being produced and moving out into the structure. And again, safety, that's the other one. Overheating being one of our biggest concerns for a heating control. Oh, okay, there we go. So that's the fan switch, that big block right there. So you can see this right here. This would be your fan switch. Behind this plate, you would have a number of controls as far as wire connections and everything like that for the system to tell the fan 3 times when it needs to operate and what it needs to do. The first operating thing that the fan's going to have is this bimetal switch, all right, this coil. All right, here's what's going to happen. This is sitting behind a wall. This is sitting in front of a wall, all right? Behind that wall is where your heat exchanger is. As the heat exchanger heats up the air around it, this bimetal coil is going to turn. It's going to turn a temperature dial inside of this, all right, inside of this switch. As it turns that temperature dial, it'll have its first setting, which will be to turn the fan on when the heat exchanger gets up to temperature. And so it'll turn the fan on once it gets up to temperature. And then once the thermostat says, yep, we're good, it'll turn the furnace off. And then the fan will stay on until it goes all the way back. That bimetal starts turning because it's cooling off, until it cools off all the way down to turn the fan off, which is the second temperature setting. So you got turn the fan on because the heat exchanger is warm enough. turn the fan off, the heat exchanger is cooled down enough. The third setting is a limit switch, and that's usually set at about 200 degrees so that if the heat exchanger is overheating and gets up to 200 degrees, it shuts the furnace down and it kicks the fan on automatically, forces the fan on until it gets back down to that cooled off temperature, and then the fan will shut off. So these are pretty interesting devices. They're old school, but they work really, really well, and they're pretty simple and basic. Again, we're going to meet up again in